All right, great. So my name is Mike Bauer. So today I want to talk about an idea that I've been thinking about quite a lot recently, and that's reprising Tomasulo's algorithm for distributed machines. I think this will be a different way, hopefully, of looking at how hardware works today, and maybe sheds light on a future direction for how we should build software. Okay, so let's look at. I want to look at how software runs on our desktop and contrast it with how it runs on supercomputers. So when I want to run, say like a scientific simulation, say I want to do a direct numerical simulation of some combustion with multiphysics chemistry on my desktop, right? First thing I do is I bust out some NumPy, start writing some nice, making some arrays. I can use nice NumPy syntax, for accessing all that data and writing my simulation. If I want to do some analysis on my data, right, I whip out pandas, I start doing some statistical analyses, some group bys on my different chemical species and stuff like that. I can pass data back into uncertainty quantification on my simulation. I can plot stuff with matplotlib. I can, automatically add scikit-learn, start recognizing, say, flame wavefronts, and then potentially rendering those with something like BTK. All this stuff kind of just nicely works together, and it all just magically works, and it runs, pretty close to the max speed that things can run on my desktop. But if I move to a supercomputer, a lot of this stuff goes out the window, right? So say if I want to run this stuff on Perlmutter, well, the first thing I have to do is I'm going to write some MPI code, right? I'm going to run different sets of computations on different numbers of nodes, running on, maybe my simulation runs on n nodes, my analysis runs on m nodes, and my plotting and visualization runs on one node. A lot of people, including myself, often end up reading and writing to and from disk in all these different places, end up being IO bound. I lose my ability to do uncertainty quantification because I can't pass data back, in real time from my statistical analyses, right? And I can't, use nice NumPy syntax anymore. My ability I have to write explicit Go cell code and manage all that myself. And so I've lost the ability to easily construct, composable software, right? This nice ecosystem that I had on my desktop is now gone, right? I have this very brittle and fragmented and difficult to use ecosystem that I have to use whenever I'm running on a supercomputer and trying to build up workflows. And I think it's worth trying to understand why that is the case and why it works so well on our desktops. And the reason it works so well on our desktops is the magic of Tomasulo's algorithm, right? And the magic of Tomasulo's algorithm is that it takes what is actually a fairly complex piece of hardware, right? Our CPU processors, even if you look at like a single Intel core, is incredibly complex, all the stuff that you've got in there. You've got ALUs, load store queues, floating point units, vector units, different kinds of register files, caches, all sorts of things. And, through Tomasulo's algorithm, we can hide all those details underneath the magic of this sequential instruction set architecture, right? And this gives me a whole bunch of benefits, right? First off, my code can be sequential, or at least it looks sequential. It doesn't actually execute like that. The hardware is actually extracting incredible amounts of instruction level parallelism out of this sequential stream of instructions. But to me, as a programmer, I just make things look like a single threaded code and just kind of, automatically gets parallelized for me, right? Additionally, there's automatic latency hiding. Different ones, these units in here take different amounts of time, right? And at the same time, the hardware is scheduling around those things. And if things are variable latency, it's automatically hiding latencies for me. It manages coherence of my data in a complicated memory hierarchy. I get composition of software, which means that if I've got like different libraries, that are composing this in single sequence of instructions, like I have a library A, B, and C, each have different routines, the hardware is looking for parallelism even across those abstraction boundaries for me, right? And I get precise exceptions whenever something goes wrong, and I get portability. I don't even have to recompile my code. If I move it to a new piece of hardware that has, different mixes of these hardware functional units, I don't have to care about that. My code just automatically uses them where it can, right? And this is really quite incredible. And I think what I want to show on the next slide is that I actually think that this is something that we should be generalizing at other scales of computing as well. So if we look at as we increase our scale of computation and scale of hardware that we're working on, I think there's an incredible amount of similarity between how the hardware works. And the reason is that it has to be hierarchical in order to actually scale. So the hardware is self-similar. So let me give you some examples of what I mean by that. If I look at like a modern GPU today, what does that have inside that modern GPU on that chip? It's got some general purpose processors, SMs. It's got a data movement unit like a TMA, kind of like the load store queue. It's got some specialized fixed function units, ray tracing cores, MMA cores, texture caches. It's got a complicated memory hierarchy and a network on chip for moving data around, right? Very similar to the single core processor, right? And so the hardware is self-similar. And this continues even up to the supercomputer scale. I look at my supercomputer like Perlmutter. I've got some general purpose cores, CPUs, I've got some NICs for moving data, I've got GPUs, FPGAs, and ASICs for doing very specialized fixed function things, and I've got, communication and memory hierarchy and stuff like that. And yet, today we have this nice, easy to use, elegant programming model, over for a single core. And we've failed to sort of learn our lesson and use this over, in the other scales of computing that we do. Instead, we, foist on users and applications people, very challenging programming models to use. They have to use explicit parallelism and explicit data movement, and explicit synchronization. And then once they've built a piece of software there, anytime that they want to try to make that piece of software work with another piece of software, it requires a massive amount of investment to kind of like stitch those things together and make them compose nicely with each other, right? And so this is just a horrible situation that we've created for application developers, and I don't think it has to be this way. So I still think Tomasulo's algorithm has a lot to offer, and we should remember the lessons that's already taught us, right? And that is that we should try to build things that provide the illusion of sequential semantics. Effectively having implicitly parallel, programming systems that actually go out there and try to provide, an implementation of Tomasulo's algorithm, such that users can have all the benefits they have on single core, processors today, at whatever scale of computing they're actually trying to do. So that's single GPU or multi GPU, or even at the supercomputer scale. Right, and I think the way you make this work, programs can just be dynamic sequences of tasks, right? You effectively have tasks that name their data that they're going to use in terms of their regions. Those tasks can recursively spawn subtasks the same way that function calls create new sequences of instructions, so you can recursively decompose at scale. And the analogy you keep in mind are just the same way that instructions and registers work for your single core processors today is the same way tasks and regions work. I think this is the way that you build hygienic and ergonomic software ecosystems, is providing implicit parallelism. I don't see any way that any kind of explicitly parallel programming system is ever going to be able to create the same degree of ergonomic and hygienic software ecosystems that we get today on single core processors. And if you still look at most of the software that is really, really successful, and I mean has millions and tens of millions of users out there, most of them are still pretty much single threaded code, and there's a reason for that. And I think, this will lead to all software eventually being, I think all software really needs to be trivially composable in order to truly be usable by lots of users. And we as a community should try to encourage that. And all software should be portable. And that's what Tomasulo's algorithm gets you. So, I think it's a way of looking at the future that I hope, maybe gets you to think about how you build programming systems a little bit differently than maybe some of the things we've seen in the past. So that's it.